Hello and welcome. Today we're diving headfirst into one of the biggest questions in all of science. It's a journey that's going to take us from this beautifully simple, almost elegant picture of the universe to absolute chaos, and then finally to a new, much deeper kind of order. I mean, really, this is the question at the heart of it all, isn't it? We've known for a while that matter is mostly empty space, with tiny little bits floating around. But what are those bits? For more than 100 years, physicists have been peeling back the layers of reality, one by one, trying to find the ultimate, fundamental stuff that makes up our world.
And what's so wild is that for this one brief, shining moment, it really looked like we had it all figured out. Back in 1932, the picture of what matter was made of seemed stunningly simple and totally complete. But, as we're about to find out, that neat little picture was on the verge of being completely blown apart.
So, let's set the stage, Act 1 of our story, the classical era. This was a time when the universe just felt logical, you know? It seemed to be made of just a few key ingredients. By 1932, the cast of characters was incredibly small. First, you've got the electron, found back in 1897. Then we figure out there's this tiny, dense nucleus, and inside it, we find positive protons. The final piece of the puzzle just clicks into place in 1932 with the discovery of the neutron. And that was it. The whole universe, from you and me to the farthest star, was thought to be made of just these three particles: protons, neutrons, and electrons. Simple, right? So satisfying. And, as it turns out, so very wrong. That classical picture, as beautiful as it was, couldn't explain everything. Almost right away, physicists started seeing some serious cracks in this perfect foundation, and it all started with a really basic question. What in the world is holding the nucleus together? I mean, just think about it for a second. The nucleus is jam-packed with protons, which are all positively charged. They should be repelling each other like crazy, trying to fly apart. So to keep it all together, there had to be some new, undiscovered force, something way more powerful than electromagnetism, but also with a super short range, otherwise we'd feel it all the time. They called it, pretty simply, the strong force.
Okay, so if you have a new force, you should probably have a new particle that carries that force. In 1934, a physicist named Hideki Yukawa came up with this brilliant idea. He suggested the strong force was carried or mediated by a new kind of particle being exchanged. And based on how short range the force was, he could even predict its mass. It had to be heavier than an electron, but lighter than a proton. He called it the meson, which basically just means middleweight.
And with that one prediction, well, the floodgates just burst open. The search for Yukawa's meson didn't lead to a neat and tidy answer. Oh no. Instead, it kicked the door wide open to this absolutely bewildering collection of new particles. The age of simplicity was officially over. Welcome, everyone, to the Particle Zoo.
So in 1937, scientists find this particle in cosmic rays that seems to fit the bill. Success. But not quite. This new particle, the muon, barely interacted with the nucleus at all. It couldn't possibly be the thing carrying the strong force. The shocking truth was that the muon was an imposter. It was basically just a heavy, unstable cousin of the electron, and nobody saw it coming. It led one famous physicist to ask, who ordered that? At about the same time, another mystery was popping up in radioactive decay. In something called beta decay, it looked like energy was just disappearing, vanishing. And that violates one of the most fundamental laws of physics. So to save the law of conservation of energy, Wolfgang Pauli proposed this really radical idea. What if a ghost particle was sneaking away with the missing energy? It would have to be neutral and incredibly light. He called it the neutrino, and it was so hard to find that it wasn't actually proven to exist for another 20 years. And then things got even weirder. Starting around 1947, physicists started seeing these new heavy particles, but they behaved so bizarrely. See, they were created really fast, in pairs, which is a classic sign of the strong force, but then they would decay very, very slowly, which suggested a much weaker force was involved. This contradiction was so baffling, they just gave up and called them strange particles. And this quote just perfectly captures the mood at the time. This simple little picture of protons, neutrons, and electrons was gone, replaced by this chaotic mess of muons and neutrinos and strange particles. Physicists were just completely overwhelmed. This quote from Willis Lamb's Nobel lecture in 1955 says it all. The neat garden of physics had turned into an overgrown jungle. But you know, just like what happened in chemistry with the periodic table a century before, a new kind of order was about to emerge from all this chaos. Physicists desperately needed a way to organize the particle zoo, and in 1961, Murray Gell-Mann delivered it with this beautiful system he called the Eightfold Way. The Eightfold Way was basically a periodic table for particles. It arranged all the known baryons and mesons into these elegant geometric patterns based on their properties like charge and that new strangeness property. One of the most amazing patterns was this one, the baryon decuplet, a triangle of 10 heavy baryons. But here's the thing, when Gell-Mann first drew it up, there was a problem. Only 9 of those particles had ever been seen. There was an empty spot right at the very bottom.
Now, that empty spot wasn't a failure. It was a spectacular opportunity. From its exact position in the pattern, Gell-Mann could predict everything about the missing particle with stunning precision, its charge, its strangeness, even its mass. He basically challenged the experimental physicists. Go find this thing. And in 1964, they did. A team at Brookhaven National Lab found the omega- particle, and its properties were a perfect match. It was this monumental triumph that proved the Eightfold Way wasn't just a convenient filing system. It was revealing a deep, hidden truth about how matter works. But that just leads to a deeper question, right? Why do the particles fit into these patterns in the first place? The Eightfold Way showed us what was happening, but it didn't explain why. That explanation came in 1964 with an idea so radical it was going to change everything all over again. The theory that all those particles in the zoo weren't fundamental at all. And this was the quark model. The big idea was that all the heavy particles, the baryons and the mesons, were actually made of even smaller, more fundamental things called quarks. To start, there were just 3 flavors of quark: up, down, and strange. And just look at their most bizarre property. They have fractional electric charges, a charge of 2/3 or -1/3. Nothing like that had ever been seen before. And the rules for building particles were just so simple. Baryons, like our old friends the proton and neutron, are made of 3 quarks. Mesons are made of 1 quark and 1 antiquark. And just like that, the entire particle zoo could be explained with just these 3 building blocks and 2 simple rules. Take the proton, for instance. It's 2 up quarks and 1 down quark. Add up the charges, 2/3 plus 2/3 minus 1/3, that equals +1. It works perfectly. The chaos was just different combinations of these quarks. But the quark model had this one huge problem. A really profound embarrassment, actually. If a proton is made of quarks, shouldn't we be able to smash a proton apart and see the quarks come flying out? Well, physicists tried. For decades, they searched and searched for a free particle with a fractional charge, and they found nothing. It seemed like quarks couldn't exist on their own, a deep mystery that we now call quark confinement. But even with that confinement puzzle, the quark model was just too good to be wrong. Over the next few decades, it grew and evolved into what we now call the Standard Model. We found out there are actually 6 quarks in total, paired up into 3 generations. And the same pattern holds for the lighter particles, the leptons, which include the electron and the neutrino. And the reason we can't see a quark all by itself, it's explained by a new property called color charge, which basically says quarks can only hang out in groups that are color neutral. The Standard Model is, without a doubt, one of the most successful scientific theories ever created. It describes how the universe works with just breathtaking precision. And yet, we know it's not the whole story. It doesn't include gravity, for one thing, and it leaves a lot of other big questions unanswered. So we're left wondering, have we finally found the ultimate indivisible building blocks of reality, or is there still another layer of the onion just waiting for us to peel it back? The quest, as they say, continues.